Good afternoon. The name of this talk is Flexible Variable Stars Extractor Software and Algorithm for Variable Stars Detection using CCD Photometry. So I will start from the brief summary of this talk. We found no solution capable to analyze a large field of views larger than 1 degree for the purpose of semi-automatic search of unknown variable sources. And as an experiment, we tested working hypotheses and implemented some well-known methods using for research of variable stars for the purpose of the search of variable stars. As the result, we obtained the software capable to check up to 40,000 stars in the field of view and 100,000 exposures in the time series. The detailed description is published in the paper, the screenshot you can see, and the deep code at the bottom of the slide. And here is the link to download the software, it's freeware. So starting from the task. Usually in the field of view around known variable source, there is about 3 to 6 other known objects. This typical field of view about 15 up to 20 minutes. Once during the observations, I had an unused camera, which was attached to the guider. Of course, not for the guiding purposes, but for the purpose of obtaining experimental series of images of the large field of view of the sky. So here is the sample image of from this camera, and the field of view is about 1 degree horizontally and a bit less vertically. There is more than 10,000 stars in this field of view, and it's not complicated to analyze all the stars to check if they are variable or not. Using Simonipack, which we used to use for this purpose. So one of the simplest algorithm is based on the dependency of noise level to mean brightness. The fainter object is, and the smaller is the SNR, signal to noise ratio, and the larger is standard error estimate. According to the statistics, if all stars were constant, the dependence of standard deviation on brightness, on the mean brightness of an object would have a parabola-like shape. If one of the stars is variable, its standard error estimate should be greater than for the constant object of the same mean brightness. So this algorithm is also implemented in the Simonipack software, which we used to use. But what we want to see and what we actually see. The left picture is from the Simonipack manual. The right picture is from the real dataset. The variable stars appeared in the cloud of the points. Some outlying points are not the variable stars, but just stars with the high noise level. Sometimes this this graph looks like this, so completely opposite that should be expected. One of the reasons why it may happen is the noisy light curve which was used. I mean that for the calculation of the standard deviation, some software uses raw instrumental magnitudes, some software use the V minus C dependence. But you may see on this chart, the red points are the raw instrumental magnitudes, and the green points are final processed magnitudes. The screenshot is made from this new software, and these are two parts of the same night observations. In one time, cloud comes, and we see that the light curve became awful. But the final process light curve, the green one, is almost normal. So the scatter is a bit higher than on the part of the light curve where there is no clouds, but it can be used. Not the red one, but the green one. So this first implementation improvement was made, we implemented the well-known method used in the MCV by Professor Andronov, the method of the multiple comparison stars. So the software calculates the mean weighted comparison star and uses it for processing of the data of the time series. So second task is to select comparison stars. Of course, it's better to select more than few comparison stars for this method. And our code selects these stars automatically, of course, giving the possibility to do it manually if the user wants. But mainly it's better to do it automatically. And there are few criteria used for this purpose. So first, this star should not be close to the border of the field, CCD field. Because the border of the CCD field has different artifacts which cannot be avoided. So it's better not to take stars close to the borders. Also, this star should be measured at least at 70% of frames. If the guiding is not perfect and some star is often disappeared from the field of view, or some faint object is often goes below the background and is not detected by the software, this is the bad comparison star and it should not be used. Also, standard deviation should not be higher than average for another stars. And also the total number of comparison stars limit. There should not be every star a comparison star. All these parameters are adjusted to the settings tab of the program. So what we got as the result? The left chart is from early version of the program, where the standard deviation was calculated from the raw instrumental magnitudes. The right chart is the same chart from the same data set, but calculated from the final green magnitudes, which you saw on the previous slides. This is not the perfect one, but let's see what happened on the next slide, the right chart. This right chart was obtained the same method, but after the filtration of the signal. So some CCD frames, which were detected as the bad frames, and some outlying points which were detected as bad points using few simple algorithms were deleted from the dataset, or let's say excluded from the dataset, and were not used for the calculation of this standard deviation. So now we see that the shape of this chart is more parabolic, so more closer to the theoretical expectations. And there are some outlying points which are suspected to be variable stars. Next, we implemented more variable detection indices. Along with standard deviation, we use chi-squared, median absolute deviation, robust median statistics, normalized excess variance, and von Neumann ratio. These are all variability detection indices which are very easy to calculate. We did not use a few complicated ones and so on. The classic algorithm which was used earlier consists of the following. We should process the CCD frames using CMONIPAC. This includes the standard dark frame, flat field correction, photometry matching. Then the analysis of standard deviation and the magnitude dependence for the raw data follows. We should note all variable stars or mark them somehow. Then on the next step, we should choose multiple comparison stars. We should choose all suspected variable stars manually because this step previous chosen stars are not safe. And then export the light curve and process it in some different software like MCV, for example, for the final time series, for obtaining the final time series. And what is the new algorithm? So CCD frames are still processed in the MONIPAC, but on the last step, instead of the analysis using the MONIPAC, you should just export varifying data using special button in the software. and then read Warfind data in our software. You can select one comparison and input its magnitude from the catalog just to have catalog values. Then decalculate mean and standard deviation for all stars in the field. The software does it automatically. Then it chooses as many comparisons as possible. You can do it manually also. The next step is to compute the star weights and make light curves for all stars in the field of view using multiple comparison star method. Then the bad frames and bad points are excluded automatically. Then the user can choose some two-channel diagram of the variability detection indices, view all outlying points, view light curves corresponding to these stars, and then export ready-to-use light curves. Here, the graphical interface of the program looks like. So the left panel contains the CCD image. The right frame contains the log data and the diagram which should be analyzed. So the first step after the opening the data file is the selection of some comparison with known catalog magnitude. Then the calculation of the standard deviation on the mean magnitude diagram with already excluded byte points. And then you can click any star on the chart or any point on the diagram and show the light curve. The light curve looks like this. The red points with error estimates are the raw instrumental magnitudes from Manipack. The green one are final instrumental magnitudes. Here the light curve is enough good, so one is not different from another one. Next, some points are marked with different symbols. For example, triangles mean that this point is bad and is not used for the following calculations. Here also you can delete some points from this light curve or delete the whole frame from the all stars light curves, all time series. You can choose and mark any star on the left or right panel as the variable one. It will be repainted with different color, like the green point. So here you can see 3 green points from the same field of view. All 3 stars are variable, and the two-channel diagrams which are shown on this slide are standard deviation on the mean brightness, chi-squared on the mean brightness, in the bottom line, median absolute deviation, and robust median statistics on the mean brightness. This slide shows the last chart on the left. This is the normalized excess variance on the mean brightness, and 3 same outlying points which corresponds to MU camelopardalis, V442 and V440 camelopardalis. The first object is an intermediate polar. Two other objects are eclipsing binary systems. On the right side of this slide, you may see the two-channel diagrams, which we use to check the stars for variability. Some of the stars, or let's say different types of the stars, are well distinguished from the cloud of points on different diagrams. For example, one star could be shown as variable on the standard deviation on the mean brightness, but another star could be in the cloud of points on this chart, but it could be, for example, outlying point on the mean absolute deviation on the mean brightness. So on the other diagram, which you did not check yet. So you can choose and check each diagram one after another and mark all points which are found to be outlined on some of the following diagrams and were not seen in the previous diagrams. So this way you will not miss the suspected variable star. And also it's easy to see the diagram of one variability detection indexes on another variability detection indexes. Like, for example, normalized excess variance on the standard deviation in the bottom. The period analysis using Klaffler-Tillman method is an optional function of this software. We had an idea to use the periodogram shape and characteristics of the periodogram for the variability detection, but we found that it's a bit complicated task, which requires much resources and is not very efficient. So we left it as an option to calculate the periodogram. That's all. And again, the link where you can download the software. There is also a brief description. There is the link to the paper where you can read about the methods used. And thank you for your attention.